Good afternoon, everyone. I'm Samson Rainey from AGU's press office, and welcome to today's press conference, Pioneering Planetary Defense: What Comes Next After DART's Asteroid Impact? Today's panelists are Tom Statler, DART Program Scientist from NASA headquarters, Andy Rivkin, DART Investigation Team Lead from Johns Hopkins APL, Christina Thomas, DART Observations Working Group Lead from Northern Arizona University, Alessandro Rossi, LICIACube Science Team Member from the Institute for Applied Physics at Nello Carrara, and Andy Chang, DART Investigation Team Lead at Johns Hopkins APL. After the presentations, we'll take questions from the media, both in the room and online. And just a reminder that this meeting is being video recorded and will be available on AGU's YouTube channel this afternoon. All right, we'll start with a short clip before the presenters take the floor. Thanks.
Earth is surrounded by asteroids. Most of them are no threat to us, but some are potentially hazardous.
5, 4.
In 2021, NASA and the Johns Hopkins Applied Physics Laboratory launched the Double Asteroid Redirection Test with the goal of smashing a spacecraft into an asteroid to change its orbit.
The purpose of DART is to demonstrate that we can protect the Earth from impacts from natural objects.
Imagine we discover an asteroid that is coming towards Earth.
Even giving it a small nudge years in advance will allow it to change its course sufficiently that it misses Earth.
DART would spend 10 months traveling over 11 million miles to its final destination, the moonlet asteroid Dimorphos, using autonomous SmartNav technology.
And at about 2.5 minutes out, we cease all maneuvering and we coast until we hit the asteroid.
Two weeks ago, NASA made history once again. And now the team has confirmed that the spacecraft's impact altered Dimorphos' orbit around Didymos by 32 minutes.
For the first time ever, humanity has changed the orbit of a planetary body.
The tail is spectacular, this amount of ejecta that you're seeing, and it's continually evolving. The observations are going on in order to fully track and watch that evolution.
It really is just the beginning of the analysis of this tremendously rich data set.
And it's very exciting to be in this position to be doing this now.
Earlier this week, NASA Administrator Bill Nelson cited the DART successful movement of the asteroid Dimorphos as one of the top 3 achievements of NASA in 2022, along with the Artemis 1 mission and James Webb Space Telescope. And so that's a tremendous achievement for DART. NASA is tremendously proud of the DART team, and that includes the engineers who achieved the kinetic impact on the asteroid moonlet Dimorphos, as well as the team of scientists, some of whom we'll hear from today, who have been collecting data, analyzing the results, and working to understand the results of this first ever full-scale test of an asteroid deflection technology. The double asteroid redirection test is a double test that was carried out at a double asteroid. First, to test our ability to actually achieve a kinetic impact with an autonomously guided spacecraft, and second, to test a real asteroid's response to that kinetic impact. The experiment was designed at this natural laboratory so that the impact of the spacecraft on the moonlet Dimorphos would change its orbit around the larger asteroid Didymos, and that orbital change could be observed using telescopes on Earth. This past October, we announced that that part of the test was successful, and the period change, the orbital period change of that orbit that was initially 11 hours and 55 minutes had changed by a little bit more than half an hour. In addition, the LICIACube CubeSat provided by the Italian Space Agency provided fantastic views in the immediate aftermath of the impact 3 minutes afterwards. Now, the DART mission exists within NASA's Planetary Defense Coordination Office, which is tasked with detecting and tracking near-Earth asteroids, characterizing them to understand their physical properties, leading the coordination across US government agencies and internationally, and designing and studying ways to mitigate the natural hazard of asteroid impact, which DART is an example, the first test of one such technology, namely kinetic impact. So before I turn it over to the panel and to Andy, I just want to explain what's happening this week. This week, the first detailed science results from the investigation team are being announced. And that's going to happen today and also at special sessions all day tomorrow that I hope everybody will be able to attend. I have seen these results. I know that they are extremely cool, and DART has been a tremendous success, as we'll see in the next couple of days. Of course, one successful mission doesn't guarantee that Earth is automatically safe from anything that might come our way, but DART is truly a giant step toward our goal of making asteroid impacts on Earth preventable and not inevitable. So with that, I'll turn it over to Andy Rivkin.
All right, thank you, Tom, and thank you for being here. It's great to be here representing a really amazing team of scientists from around the United States and around the world. And catching people up on what we've been up to. During the trailer, you heard one of our scientists, the coordination lead, Nancy Chabot, talk about ejecta, and a lot of what you're going to hear about today relates to that ejecta. We had to plan for a situation where we didn't have much, but it turns out that we have quite a bit. So that's given us a lot of great things to study. So the first thing I'm going to show here, and let's see if I can tell my next from my back. So this is an animation. This is a movie from the very end of November. This was taken at Magdalena Ridge Observatory in New Mexico. And it's representative of what a lot of the astronomers on our team have been doing and seeing for the last several weeks, and actually longer since the impact occurred. So what we see here is Didymos in the center of the frame, the Didymos system. So both Didymos and Dimorphos appear as a single point of light. You see a tail stretching off to the upper right there. And that tail is made of material that was blasted off of Dimorphos from the DART impact. The tail goes off and it stretches off the edge of the frame there, because of course we want to center the frame on the Didymos system. So we see the tail stretches off. We know it's tens of thousands of kilometers long. So it goes most of the way around the circumference of the Earth at a minimum, if not longer. So we're thinking maybe 30,000 kilometers, maybe longer. The next thing I'm going to show, this of course is again a movie of it moving across the sky, centered on Didymos, so the stars move past. If we take several of those images and we add them together, we can get the equivalent of a longer exposure. What that means is that the stars, which we're moving past in the movie now, are kind of seen as a string of ducks. But this again is just a view that lets us see a little bit further, get a little bit more detail, and we can see this long linear feature, which is again the tail. The next thing I'm going to show takes averages like this, and now every frame is going to be an average from one single night. This shows the data taken over several weeks from late September through to late October. And this was taken from our colleagues and team members in New Zealand at the Mount John Observatory. And here you can see near the start, there's these features going off to the top and to the lower left. And then as the nights go on, those kind of disappear and the tail gets longer and swings down to be more horizontal. These changes can be tied to the material in the in the tail, smaller material moving more rapidly under the influence of the solar radiation pressure. Larger particles take a little bit longer. So by studying how these changes occur and the time scale on which they occur, we can get a handle on how much material is in that tail. The smaller material, just for context, there is we're talking sand size, dust size. Larger material, we're talking maybe fist size. So we're not talking about podium size or larger. We can use this in several telescopes coming at this problem in a few different ways to come up with an estimate of how much material was blasted off of Dimorphos by DART. And we think it's about 1 million kilograms of material at the least. So this is enough to fill 6 or 7 railway cars of gravel and material. The studies are still ongoing. It may be that number is a minimum. It could be twice that. It could even be as much as 10 times that, according to some estimates. So these studies, allow us to tie into natural phenomena like icy comets, or like the kind of active asteroids that we see that are naturally getting hit by impacts out there in the solar system. So we expect the tail to continue to change. We expect it eventually to fade, but we're not sure how long that's going to take. So we're going to keep these observations going as long as we can. And I'm sure that astronomers will also be looking the next chance they get in 2023 and 2024. So with that, I will pass this off to my colleague, Dr. Christina Thomas.
All right. Hello, everyone. So it's my pleasure to talk to you about some of the other kinds of observational results that we have. And I'm here essentially on behalf of a very large team of observers that have been doing all sorts of various kinds of observations, including the ejecta that you just saw. And so I'm going to speak a bit about the composition of Didymos and Dimorphos. And this is part of a big effort that we have to understand the physical properties of the system. And so one of the open questions that we had going into this was whether or not the two objects had the same composition. It was an assumption that we made based on how we understand the formation of binaries, but it had not been confirmed. And so we were able to look at the spectra that we took around the time of impact to investigate this question. And so here you see a graphic that essentially illustrates what we were looking at before the DART impact. And so we are looking at the system. So both of these objects appear to us as a single point of light. And so you could see that here. And the observations that I'm going to show you are from the NASA Infrared Telescope Facility, so the IRTF, which is on Mauna Kea in Hawaii. And so we used the SPECS instrument to get near infrared spectroscopy. So looking at how the reflected changes over the infrared wavelengths. Before the impact, all of the light that we get from that single point of light in the sky is about 96% Didymos. And so Dimorphos is a very, very small fraction of that reflected light. But let's see. After impact, we threw a lot of Dimorphos material into the system. And so you could see here an image from LICIACube, which is kind of demonstrating how much of that ejecta has gone up into the system. And so while it's not exactly a single point of light anymore, it is still looking to us to be approximately that. But now the scales have shifted, and approximately 2/3 of this reflected light is Dimorphos material that had been ejected off of the surface. And so we can use these two observations at these two different time periods to compare the spectra. And so here is the pre-impact near infrared spectra. And again, this is from the NASA IRTF. This is very typical of what we call an S-type asteroid. And so it has these very large absorption features at about 1 and 2 microns. And so this is what it looks like in the pre-impact case. And this is what it looks like in the post-impact case. And so again, now we're looking at the majority of the material being from Dimorphos, and you'll notice that the two spectra look very similar. They have a lot of these consistent features, specifically these large silicate bands at 1 and 2 microns, which are consistent with it being an analog for something like an ordinary chondrite. And so we're very excited to see that these two objects are in fact similar in composition. You'll notice that there are some slight differences that are tied to a lot of other questions that we're going to be investigating in the coming months. But they do not actually impact the way that we think about it compositionally. All right. And now I will pass on to Alessandro.
Hello, everybody. It's a pleasure being here as well. As was mentioned, the Italian Space Agency LICIACube probe traveled for 9.5 months in the safe womb of the DART mothership and was released 15 days before the impact. It started science operation 71 seconds before impact, passing as close as 58, more or less 58 kilometers from the system at closest approach, and took unique images of the event. Here you see enhanced color images taken. The left one was taken about 3 minutes after the impact, and you clearly see on the bottom right the ejecta plume coming out of Dimorphos. We are looking at the south pole of Didymos, and you see the ejecta cloud almost face on. A few seconds after, LICIACube has moved, and we see the plume from a different perspective, and we can clearly notice the cone shape of the ejecta coming out of the surface of Dimorphos, and we also can notice a kind of dark arc over the surface of Dimorphos, which we believe is related to the shadow of the plume itself on the surface of Dimorphos. Playing with the raw images, we can enhance the level of saturation of the images. And in this image, you see the saturated part of the image in black, but in that way, other features of the ejecta plume come to your vision. And here we clearly see some very interesting structure in the ejecta plume. You see linear filaments of material being ejected from the surface, but we also see clumps of materials possibly related to agglomerates of particles or to particles in the process of being disrupted, and also nodules that we attribute to the presence of larger boulder being ejected. Looking at images at different times, we are able to compute the velocities of these objects, which we account on the order of tens of meters per second in these cases. The LICIACube carried 2 cameras, a narrow field one named Leia and a wide field one named Luke. Luke has 3 filters working at different wavelengths, the red, the blue, and the green part of light spectrum. And looking at the difference in colors and the ratio in colors, we know that this gives us information on the composition of the bodies and also on the size of the grains we are observing. So we can do also quantitative science, and you can see in the image passing from the monochrome one to the color one on the right, you can see different level of blue and red line that tell us that probably, for example, in the blue part, we have very small particles of a micrometer size, and in the red part, we are probably observing material which has been more altered due to space weathering from the surface of the asteroids. This is important, in our opinion, to show that you can do a very good science also with an extremely small spacecraft. You see the image, LICIACube is a really small spacecraft, And it's proving that we have an avenue of possibilities by using CubeSats even in deep space. And as a matter of fact, in a couple of years from now, ESA is launching the Hera mission. We will go to the very same Didymos Dimorphos system to explore in depth what happened, and it will release 2 CubeSats, Juventus and Milani. We will go deeper in the examination of the system and even try to land on the bodies. Thank you. And I leave the floor to Andy Chang.
All right, thank you. Well, I'm going to come back to DART as the Planetary Defense Test Mission and hitting the asteroid with the spacecraft to change its orbit. So what I'm going to talk about is the momentum transfer. Momentum, when you transfer momentum to a target, you're going to change its velocity, and that is how you change an orbit. So what I'm going to announce is the amount that we have changed the orbit in terms of how much momentum did you transfer to the target. So let me just start the animation. If you have a simple collision on the left where you just hit the asteroid, you don't make any ejecta, your projectile ends up inside somewhere the target, then the amount of momentum that you put in the target is exactly equal to the momentum that the spacecraft came in with. But if the collision actually produces ejecta that we have seen, if it produces ejecta, you blast material off the target, then you have a recoil force. The result of that recoil force is that you put more momentum into the target. You end up with a bigger deflection. So if you're trying to save the Earth, that makes a big difference. That's what we're going to come back to, because you want to be able to deflect the asteroid enough to make it miss the Earth. You also don't want to make it, you don't want more deflection than you need. That would be wasteful. And you definitely don't want too little. Okay, so what happened with DART? What happened with DART is shown here, that the amount of momentum that you put in as quantified by a momentum enhancement factor was 3.6 times greater than what the spacecraft originally brought in. So the effect of the ejecta was actually larger than, considerably larger than what the direct transfer of the momentum from the projectile. So this is very good news for kinetic impact technique. It says that at least in the case of DART, the kinetic impact on the target was really efficient at changing the orbit of the target. And the factor of 3.6 applies in the case where the target, Dimorphos, and its primary body have the same density. And the density we need in that case is about 2.4 times the density of water, so 2.4 grams per cubic centimeter density. In that case, then the momentum enhancement factor is 3.6. Now, DART did not actually measure the mass of Dimorphos separately. The result of all the observations and measurements that DART and the ground-based observations of the system, what they determined is the total mass. So it's the mass of Didymos and Dimorphos put together. That mass is accurately known, but we don't know whether the two bodies have the same density or different densities. So both of them having the same density is certainly plausible, certainly likely, as we have heard. The two bodies have the same composition, and that composition is that of a kind of meteorite we have called ordinary chondrite. And those meteorites are in fact pieces of asteroids that were blasted off by natural collisions, and they have fallen to Earth. And so the density of 2.4 would be consistent with that composition if it's not in the form of a single intact large rocks, but broken up into pieces, so that there's actually empty space between the pieces as they sit together on the asteroid. So why do we care about the momentum enhancement factor being 3.6? Let me just illustrate. Suppose you had a situation where an asteroid is coming toward Earth and you know it's going to hit. Okay, there isn't any such now, but we have figured out that, okay, if we have a kinetic impactor, we can expect there's no momentum enhancement. So the momentum enhancement factor is 1. Turns out we can just barely get the asteroid to miss the Earth, but we have to hit it 18 years out. So you need, in that case, say a lot, enough warning time to be able to put a mission out there to hit the target 18 years before it would hit the Earth. So 20 years of warning time, maybe. But if the momentum enhancement factor is 3.6, you could use that same kinetic impactor and same target, and you could do your interception 5 years out instead of 18 years out. So you need less warning time. Also, the momentum enhancement factor could mean that if the target turned out to be 3.6 times more massive than you thought, or if it's a bigger target, you would still be able to make it miss the Earth. Or alternatively, if we knew all this in advance, you could say, okay, I could use a smaller and less expensive kinetic impactor to do the job. So this is why the measurement of the momentum enhancement factor from the DART impact is perhaps the most important piece of information we can take away to use in a future planetary defense scenario, because that's what you need to be able to design a mitigation technique. Okay. So back to, I guess, Samson.
Thank you so much for that presentation, panel. We'll now open it up to questions from the media, both in the room and online. Before asking a question, please state your name and your media affiliation. And if you're online, you can either request to be unmuted or type your question into the Q&A chat box. I'll start with in the room.
Thanks very much. It's Jonathan Amos, BBC News. Andy, that 18 years that you talked about, is that a number you've just plucked out of the air, or is that a number related to an object, like Dimorphos that's on a collision path?
It's a number plucked out of the air.
Right. Okay. Has anybody done the calculation on a Dimorphos-like object?
Well, many people have, actually.
Yeah, coming towards the that's 7 minutes you need.
So,
right? 7 minutes.
If I can just elaborate on that. I mean, any situation that we might find ourselves in the future would be a unique situation. And so any example that we give now, including Andy's 18-year, 5-year example, is just a toy example. It's one particular orbit chosen, one particular circumstance. The reality in a real situation, if we needed to deflect an asteroid, would depend on the orbit of the asteroid. It would depend on the circumstances of the encounter, what kind of geometry we could achieve with the launch from Earth at a given time. And so any numbers like that really should just be taken as one typical example, one toy example. And for a real situation, we would analyze that specific situation and determine exactly what would be needed. Didymos and Dimorphos is not really a good toy example because, of course, the whole geometry, the mission itself of DART was done in order to get good data back and have the collision occur close to Earth, which is not necessarily what we would have done if it had been a deflection scenario. So, if you want numbers for a specific case, we would want to take that specific case and work that.
It's just to help us understand the reason why this is an important measurement for planetary defense.
Yeah, and at the risk of confusing by elaborating further, but hopefully not. You mentioned 7 minutes, so we should make the distinction between the amount of time you would change the period, which in this case would have been 7 minutes without ejecta, versus the amount of warning time you would need to launch, to be able to make the change you need, which is measured more like years to decades.
We have a question online.
Yes, we have a question from Megan Bartels for space.com for Andy Cheng. Do you have any estimate of the original mass of Dimorphos to compare that 1 million kilograms of ejecta to?
Yeah, does anyone happen to remember that number?
Yeah, this is Andy Rifkin, also of APL. Our estimates were that the original mass of Dimorphos is something like 5 billion kilograms. Yeah. Maybe it's 4, maybe it's 6, but it's more like that. So we're talking about a tiny, tiny fraction And even if the 1 million kilogram ejecta is low by a factor of 10, it's still a very tiny fraction of the
5
original.
times 10 to the 9 kilogram. Yeah.
Any questions in the room?
Sorry, I'll keep going if I may. I mean, this was almost perfect, right? I mean, you hit it smack on the head, didn't you? Yes.
Yes.
So, I mean, from that point of view, that must have really helped with these calculations, yes, and these observations, is because you had an almost perfect experiment.
Yes.
I can, this is Tom Stanler, I can add a little bit more to that. I mean, in addition to having great geometry and fantastic performance, the SmartNav system that enabled DART to hit essentially a dead center, we also have the fantastic images from LICIACube and the analysis that's gone on inside the investigation team to interpret those images and see the geometry of that ejecta cone and what that's telling us about the direction of the ejecta and how that was pushing the body. That's really been indispensable for this analysis and getting such a clean result so quickly after the event.
And we have a question online.
Another question from Megan Bartels at space.com for Christina. So far, has there been any sign of changes in the relationship between the asteroids or the wobbles or some other less dramatic changes that were possible?
Can you repeat that?
So far, have there been any signs of changes in the relationship between the asteroids or the wobbles or some of the other less dramatic changes that were possible?
We'll hear about it tomorrow.
So actually, that's going to come up a bit in some of the talks that we have tomorrow. And so it's something that we're currently analyzing. We have some data that is looking at the new orbit of the system and how those two bodies are related to each other. And of course, for the light curve observations, which feed into the orbit analysis, those will be ongoing until March of 2023. And so some parts of this is a very long-term analysis question.
Zach Savitsky, Science Magazine. So you've illustrated that the momentum enhancement factor is affected significantly by the internal structure of the asteroid. Is there any hope for assessing the internal structure of an incoming asteroid before running into it so that we have an estimate of how the momentum will be impacted by that factor?
Yes, that's another area that's being investigated. It's being done by numerical simulations, basically assuming different kinds of structures and seeing whether we can reproduce the results of the DART impact. So not only the amount of beta, but the amount of ejecta and things like, and the period change. But sorry, the amount of the momentum enhancement and things like that. So yeah, that is an area of investigation. The only way you're going to find, I mean, that's one of the few ways that you can find out about the interior is to actually hit it with something. Otherwise, the Hera mission will be going to the same target and will be making both gravity measurements, which will be a way of probing the interior, as well as radar, or ground penetrating radar measurements.
And we have another question online.
A question from Jeff Faust at Space News. What factors in the composition or structure of Dimorphos might explain the value of beta you measured from the DART impact? Would larger asteroids or those with different compositions have larger or smaller values?
Very good question. Probably cannot answer. It's an area that people are, this is again an area that we are investigating, we're working on. And so, yes, yes, it will depend on composition. The value, the amount of momentum enhancement also depends on the internal structure, how much rubble there is, how it's packed. So yes, it's something we're working on.
Yeah, this is Andy Rifkin, APL. This is, we have a first data point. We have another partial data point in that the Hayabusa 2 mission conducted a small impact experiment at Ryugu, and that's a different kind of asteroid. So as my colleague Andy Cheng said, we'll certainly be comparing, and the community will be taking data and comparing. There are a lot of factors that go into this, not just composition, but as Andy said, density, near surface density, whether you hit a big rock or not, the angle you came in. So
this is Tom Statler continuing to riff on that theme. So there are a lot of parameters other than composition, as both Andy's said. There's porosity, there's chunkiness, there's density, and so on. And the impact modeling team is working on surveying that space of parameters and understanding what combinations of density and porosity and so on and composition would be consistent with the result that we get. Having done that, which is still work in progress, that'll be finished in the future, then making the connection between those properties and what could be observed from the outside, as Andy Cheng was talking about, to be able to give us a way of in any future situation to be able to observe an asteroid surface and infer enough about what's going on in the interior to tell us what kind of dynamical response would happen. That's on track to continue work on the DART team and on the HERA team. But that is exactly where we're trying to get, is to have that ability to observe an asteroid both from the ground or maybe with a reconnaissance mission and infer what the response will be if we do deploy a kinetic impactor against it. So it's a great question, definitely work in progress.
Hi, Morgan McFall Johnson from Insider. I wanted to ask about the LICIACube images, give you an opportunity to talk about if there was anything especially surprising or unexpected in those images or about them. You mentioned large boulders in the ejecta. I'm curious how large they are. And then I have a question after.
Yes, the images were indeed impressive, and we didn't expect some of the feature what we see. About the size of a boulder, we are working on that. It's pretty difficult at the moment to say a number, and I will not guess any number right away, because we have, as was mentioned, we have to exactly calibrate the distance where the images were taken to identify all the features. But these are all characteristics that we should be able to find out pretty soon. And yes, and it's important to say that now we have a vision of the ejecta plume from close by. We have a vision from the ground. We have a vision from Hubble Space Telescope, from James WST telescope. So we have a lot of different geometries to compare with, and this is allowing us to clearly characterize the ejecta plume from many points of view. So stay tuned.
And then I'm curious, would there be any value to sending a CubeSat mission of this type alongside a real deflection mission?
Well, for a kinetic impactor, of course, the mass is important. So it's not going to be, let's say, the projectile. But as a witness of the event, certainly it's going to be extremely important. And they will be important again, as I mentioned, in the ERA mission to characterize the system and to give many of the information that were asked in the question that were raised before. That is the densities of a body, the internal structure, and so on and so forth. So they are definitely important. Of course, they cannot be the projectile for the kinetic impactor. They are too small.
And we have a question from online.
Question from Dan Clower at vision.org. Would the addition of an explosive impact, potentially a nuclear impact, affect momentum change by creating more ejecta?
Yes, but you want
So this is Tom Statler. A few things involved there. So first of all, one of the reasons that a kinetic impactor works in the first place is that the impact occurs at high velocities. And at the DART impact speed of 6.1 kilometers per second, the spacecraft carried far more kinetic energy than an equivalent mass of high explosive. So there would be no benefit of adding a chemical explosive to a kinetic impactor. It would just increase the complication. You'd have to deal with the explosive materials and launch it and so on. And you might as well just put more mass because it carries more energy just by the fact that it's moving. Now, a nuclear explosive takes us into a different category of deflection technique, which is also being studied, but which isn't kinetic impact. And in that kind of a deflection scenario deflection approach, the idea would be to explode a nuclear device not at the surface of the asteroid, but near the surface of the asteroid, not with the intent of destroying it, but with the intent of vaporizing part of the surface, which would, because it was hot and vaporized, quickly blast itself off the surface of the asteroid and, akin to the recoil effect, push the asteroid in the other direction. It's a way of creating more ejecta over a larger fraction of the surface of the asteroid than a kinetic impactor would. But all of that is under study, and it would be a different approach.
And I guess just for the record, Andy Rifkin, APL, for the record, a test of that technique is illegal under international law.
Any questions in the room? We have another question from online.
Yes, we have another question from Megan with space.com for the panel. I know that the momentum enhancement factor was a key number to get. How are you feeling now that you have that value?
We feel great.
It's great to have it out there. The job is still, it's great to share it. And we have a lot of great work still to be done by members of the team to further study that. And that's very important work. And, we look forward to sharing that with you as well as we get into those details and can put better bounds on this. But yeah, as noted, this is one of the main requirements of the mission was to come up with what this number is. And now that we have a first, kind of number to share, that feels good.
All right, I'm going to jump in there for a second too. So this is Christina Thomas, NAU. And it's really, really exciting from an observation standpoint to be here where we have the period change measured and we're actually improving our accuracy every day. And so from here, now we actually get to our dream list where we can start to think about the really complicated dynamical effects that were predicted that we weren't sure that we would be able to observe because we'd never done this before. And so we are looking forward to more observations that are going to allow us to study things in great detail. And I think that's a really exciting place to be.
Thanks. Yeah, I'm just sort of kind of following on really. What do you really want from HERA? What are the data points that you really want? The information that you need to finish your job?
Well, we could start with measuring the mass of Dimorphos. And then also if there's a crater to measure, well, to see if there is a crater. And to see how big that crater was, basically to be able to determine the amount of ejecta, independent measurement. We want to see what the shape of the two bodies is, because DART is only able to measure a small portion of the surface, less than half of the surface of either body. That was what we were able to see. So shape of the whole bodies, how large they were, what was the mass? Also dynamical effects, all the changes in the orbit. So not only the period change, but eccentricity as well is important, as well as the changes in the rotation state of Dimorphos, because the DART impact is going to change the rotation of the body. We don't know actually accurately what the rotation state was. It turns out that doesn't affect the momentum transfer calculation very much, but it certainly affects our understanding of exactly what the dynamics of how that was affected by the DART impact. So, and internal structure, yes, thank you. Alessandra reminded me, yes. Internal structure of the bodies as well. So from radar measurements, from the gravity measurements of CubeSats, by the way, carried by Hera mission. So there's a whole lot to look forward to, all kinds of things. Almost can't wait.
Great. Any other questions in the room? Any questions online? If there are no further questions. Thank you, panel. That was great.
Planetary defense rests.